Previously, I asked you to show that the sum of two consecutive integers was even or odd. And in my solution, I showed that if we started with an odd, the next consecutive integer is even. And without loss of generality, you could have started with any even number and proven that the next consecutive number was also odd. If we wanted to write a complete proof for the parity of two consecutive numbers, though, we would need to do so using cases. And I just used a term you may not have heard before, and that is the term parity. So let's discuss that first. So what is parity? The parity of an integer refers to whether that integer is even or odd. So 27 has an odd parity and 22 has an even parity. So we're going to use this idea, this concept of parity, to help us prove that any two consecutive integers have opposite parity. So we're going to use a proof with cases. So we're going to divide our proof into cases so that we can show that our property is true. We can prove then that any two consecutive integers have opposite parity. So let's start with our statement, which is not going to be any different from any of the statements we've used before. So our statement here will be that for all integers m and n, right? Make sure, here, let's see here, let's make a good integer. There we go. For all m and n in Z, if m and n are consecutive, and remember we defined that for ourselves earlier, then m and n have opposite parity. So that is what we are trying to prove. So let's get to our proof. The only thing we can really suppose first off is we're going to suppose that m and n are integers such that m and n are consecutive. In case we have someone reading our proof that doesn't know what consecutive means, we're actually going to go ahead and add in a definition for consecutive for our reader. So we would say by the definition of consecutive, I wish I could write as quickly as I speak. By the definition of consecutive, we would say that n is equal to m plus 1. And by the parity property, which is what we just described above, by the parity property, m is either even or odd. It is either even or odd. So that's where we start. So this supposition here, where we start our if P then Q, so this is our P, if you will, all of the wording that we have here is what's setting up our cases. Typically for our cases in this class, we're going to be looking at even and odd. We're always going to be looking at parity. We will get into cases a little bit with some of our set proofs possibly out in chapter 6, but for now, for all this chapter 4 stuff, all of our cases are going to be related to parity. So you will want to reference the parity property in your supposition phase, in your hypothesis phase of your proof. So you want to include by the parity property, m is either even or odd, because now those are our two cases. So I'm going to put them in different colors so you can see where the two cases are, but you don't have to do this. So for case 1, we're going to suppose m is even. And then for case 2, I'll put that one in blue, we will suppose m is odd. And we have already said that m is an integer, so we don't have to repeat that here. So let's look at case 1 where m is even. And you notice I put mine in columns because then it makes it a little easier to make sure you haven't skipped steps if you do one and then the other. So we're going to suppose m is even. Just like any other section 4.1 and 4.2 proof, we would start by saying that by the definition of even, we know that m equals 2k for some k in the set of integers. So moving into the part where we have to prove then that n has the opposite parity, we need to jump into our by substitution. So by substitution, n is equal to m plus 1. And we know m is 2k, so we get that n is equal to 2k plus 1. Well, that just happens to be the definition of, you guessed it, odd. So let's make it very clear for our reader that that's exactly what is happening in here. We would say then that thus n equals 2k plus 1 for some k in the set of integers, which just happens to say then that we have the definition of odd. So by the definition of odd, we know that n is odd. And notice I'm not going to put a QED here because we aren't actually finished with our whole proof. We're only finished with the first case. Let's try the second case. We're going to suppose m is odd. And we'll say by the definition of odd, we know then that m is equal to 2k plus 1. So what we need to do next is say that I know by substitution that n is equal to m plus 1. And m here is 2k plus 1 plus another 1. So we get 2k plus 2, which is 2 times the quantity k plus 1. At this point, you might be wondering why I can reuse k. Because I mentioned back in 4.1 and 4.2 that you cannot reuse the same variable. Division into cases is a little different because each case is a self-contained proof. So you have a proof within a proof for each of these cases. So yes, you can use the k within each case if you want to use the same one. If you do not want to use the same one, you can use L or P or Q or some other variable letter that you would like to use here. But I'm going to finish it out using k. So now we have 2 times the quantity k plus 1. So let's let p equal k plus 1. And then we know p is an integer because integers are closed under, and I hope you said, addition. So thus, we have that n is equal to 2 times p for some integer p. And that sounds like the definition of, you guessed it, even. So we would say, therefore, by the definition of even, n is even. So you notice we have now proven both cases, and I will say there is always one that's a little bit longer than the other, and it's usually the odd case that's a little bit longer than the even case, because the odd case has the 2k plus 1, and the even case just has 2k. But now that we have proven both cases, we need to write one conclusion to sum it up. So I think of it sort of like in Lord of the Rings, they have the ring of power. We have to have a conclusion to rule it all. So nerdy, I know, but it helps to drive the point home. So we will say then, it follows that regardless of which case occurs for the particular m and n, one of m and n is even and the other is odd. If you wanted to say it follows that regardless of it follows that regardless of which case occurs, I just realized I forgot a word, which case occurs. There you go. For the particular m and n, you could say when m is even, then n is odd, and when m is odd, then n is even. You can also write it out that way. Let's do one more proof with cases. So oftentimes you're going to ask, how do I know I need to divide my problem into cases? And again, that's going to come down to, are you talking about evens and odds? Are you talking about the parity of a number? So let's prove that for any integer n squared minus 5n plus 75 is odd. So it says for any integer here, and then it talks about this sum and difference and product of integers is odd. So that's generally a good indication that you're going to need to break your proof into division by cases. So let's start with our statement as always. So our statement as the universal conditional says for all n in the real numbers, if n is an integer, right? If n is an integer, then n squared minus 5n plus 75 is odd. So in our proof, we're going to start with just supposing n is an integer. And then what we know then is that by the parity property, n is either even or odd. So let's break it up into our cases. So case one, let's suppose n is even. And case two, we will suppose n is odd. So let's start again with the even. I always do even first and then odd. It doesn't matter which order you put them in, as long as you cover both cases. I just have a habit and stick with it. So let's suppose n is even. So then by the definition of even, we know that n is equal to 2k for some k in the set of integers. And then by substitution, we can say then that n squared minus 5n plus 75 is going to be, well, everywhere we have an n, plug in 2k. So 2k quantity squared minus 5 times 2k and plus 75. You can already see where this is going to get a lot longer when we do this with an odd, because we're going to have some binomial multiplication. So we end up with 4k squared minus 10k and plus 75. And now remember, we're trying to show that this expression is odd. So that actually isn't going to be a bad thing, because we can break up that 75 into 74 and 1. And now we can pull out a 2, not a 4, not an 8, no other kind of even number, only a 2 can you pull out when you're factoring. 2 when you're trying to show even or odd. So 2 times, and we're left with 2k squared minus 5k plus 37. And then we'll add a 1 at the end. So now to continue our proof, let's let p equal 2k squared minus 5k plus 37. Then we know that p is an integer, because integers are closed under, well, let's see, what all do we have? Addition, subtraction, and multiplication. We got them all. So So thus, if we continue our simplification, we have n squared minus 5n plus 75 is now equal to 2 times p plus 1 for some p in the set of integers. And that sure sounds like the definition of odd to me. So by the definition of odd, n squared minus 5n plus 75 is odd when n is even. Now we're going to repeat the entire process for case 2 with supposing that n is odd. So try to pause here and do it on your own, and then come back and check your answers. Well, I hope you tried this, and I hope that you've figured out that when you square a binomial, it has 3 terms, not 2. So we'll get to that. Let's start with supposing that n is odd means that by the definition of odd, we know then that n is equal to 2k plus 1 for some integer k. And now by substitution, this is where things get fun. N squared minus 5n plus 75 is now going to equal 2k plus 1, quantity squared, minus 5 times the quantity 2k plus 1, and then plus 75. So this is when you have to remember that 2k plus 1 times 2k plus 1 is a trinomial. It is 4k squared plus 4k plus 1. We have minus 10k, minus 5, and plus 75. So if we put together some of our like terms, we end up with 4k squareds, and we have what? 4k minus 10k gives us a negative 6k, and 75 minus 5 gives us 70, and then plus 1. So I'm going to do plus 70 and plus 1 because we need to show that it's odd anyway, so why not leave it as 70 and plus 1? So we end up, when we factor out our 2, we get 2k squared minus 3k plus 35, and then we still have our plus 1. So we will let p equal 2k squared minus 3k plus 35. Then we know that p is an integer because integers are closed under, and we have all 3 again. We have addition, subtraction, and multiplication. So continuing our simplification, we would say thus n squared minus 5n plus 75 is equal to 2p plus 1 for some p in the set of integers. And therefore, by the definition of odd, n squared minus 5n plus 75 is odd when n is odd. And then remember, we have to have one conclusion to wrap it all up. So our final conclusion would say, it follows that regardless of which case occurs, n squared minus 5n plus 75 is odd for any parity of n. And it has been shown. And that's the end of section 4.5.